Confidence intervals explained. Confidence intervals, and from that p-values, are one of the most important ideas in statistics for you to understand statistics, for you to use statistics for other scientific disciplines. Now, I'm going to show you this app which I've developed to help you to understand and visualize confidence intervals. Here at the very top we can find the URL for the app, and it also has this video here which we're watching right now. Here is the problem. The problem is that in statistics we are measuring people, we are collecting data from samples. The problem is that we don't actually care that much about the sample. Often we are just using the sample to find out about the population. So let's imagine we want to find out about the average height of all the people. The average height of all the people. The problem is we can't measure all the people. What we can do instead is we can measure a sample. We can measure 100 people for one sample, and maybe another sample of 100 people, and maybe another sample of 400 people. But the problem is that what is true of the sample is not necessarily true of the population. So maybe the average height of all the people of the population is 165 centimeters, but in the sample it could say it's 160. And then we have different samples, and different samples could tell us different things. So one sample could say that the average height is 160 centimeters, another one could say 180, another one could say 192. Different samples are telling us different things, and what that means is it's actually surprisingly difficult to work out what is the actual average height. But what we can do instead is we can say, well, we don't know the average height, but we can find out the range in which that average height is going to lie. So what we have here, first of all, what you can do in this app is you can set the parameters, so the numbers that describe the population. You can set the standard deviation of whatever you're measuring. You can set the population mean, and what it does here is it simulates, that means makes up numbers from 8 different samples of 100 people, and then it plots it here. And what we can see is these 8 different samples from the population end up telling us 8 different things. So this is really the way of coding it. What we're doing is essentially we're starting with the population, and we've taken 8 samples, and each sample has a different shape, and they're all on top of each other here. There you go, samples 1 through 8, and they have a slightly different mean. So the question is, how do we actually know what the population mean actually is if the samples keep telling us different things? Well, what we can do is we can look at something called a sampling distribution. So we know about the distribution, we know about the mean, we know about the standard deviation. If you want to revise those or learn about those things, you can look at our descriptive statistics toolkit. But the basic idea is that we have a list of values, let's say a list of 100 heights, for 100 people, and we can plot that as a distribution, right? So the distribution would be the heights of 100 people. But let's say we don't just sample 8 samples, we take 100 samples or 1,000 samples or 10,000 samples, and let's imagine we had a big list and we recorded the means for all those samples. So we write down the mean for sample 1, the mean for sample 2, the mean for sample 3, and we do that again and again and again and again and again for thousands of samples. Then we could actually take those means and plot those means, here it is, as a distribution. So if you go to the top here for distribution display, you can change what's being shown. And what that means, this is a distribution of these different heights. So we've got not heights of sample means, it's a distribution of sample means. We've got most of the means are up here. There you go, the average. Here, what is that, 89. And the further you move from the average of the averages, the fewer there are. So there aren't many samples with this mean, there aren't many samples with this mean. And the good thing is the sampling distribution, even if the variable itself is not normally distributed, the sampling distribution will be So this is always normally distributed. And the good thing about that is that we already know the rules for the normal distribution. So we know that the rules for the normal distribution is that about two-thirds of the data will be within one standard deviation of the mean. We know 95% of the data will be 1.96 standard deviations from the mean, and we know that about 99% of the data will be around 2.5 standard deviations from the mean. Now, the principle is the same here, but when we're looking at a sampling distribution, we don't call it a standard deviation, we call it something slightly different. We call it a standard error. Let me show you that. So standard error just means the standard deviation of the sampling distribution. And so what that means is that we have all these samples and we measure the means of all these samples, and 95% of the means will be around there, 67% of the means will be here. So this blue line is the mean plus one standard error, and this blue line is the mean minus one standard error. So the standard error is just the standard deviation of the sampling distribution. It's how far the means are away from each other. And it actually depends on two things. So it depends on how widely spread is your variable. So let's imagine that if it was a variable which didn't have much variance, didn't have much standard deviation, then the narrower the deviation of our variable, the closer the means are going to be to each other, and therefore the skinnier our distribution, the narrower our standard error. And the other thing is that the larger our sample size, the smaller our standard error as well. The larger our sample size, the smaller the standard error. Why? Because the more people we measure, the closer our samples actually get to representing the whole population. The sample gets closer to the population. And so the equation for standard error is just variance, that's standard deviation squared, divided by sample. Another way of saying that is standard deviation divided by root of sample. But once you know the standard deviation of the variable you're measuring, and you know the sample size, then you can work out your standard error. Now, what you would want, and actually what it does here is it shows you your standard error here. You want that standard error to be as small as possible. We can also show it back on our 8 distribution. So we go back to our 8 distribution. So if we have a variable which has a high standard deviation and a very small sample size, we can see that all of these different samples are showing very different things. However, if we change that, if we reduce our standard deviation and up our sample size, then we suddenly see now our variables are our sample means are more similar. These samples are showing us more similar things. Now, we can't actually change the standard deviation of our variable, but the point is that this is why it's important to get a good sample size, because the bigger the sample size, the smaller our standard error. So far we've got to standard error. Let me just change that a little bit so it's easier to see. Now, once we have our standard error, what we can actually do is we can create something called a confidence interval. So let's imagine that we have performed a study, and in our study we have said, look, in our study we found, let's actually just change the mean so it's a little bit easier. There you go, the mean's gone to 50. In our study, we know that our mean of our variable is 50. In the sample, we want to find out the population mean. The mean in our sample is 50. And we know the standard deviation and we know the sample size, and that allows us to work out our standard error. So now we know what our mean is and we know what our standard errors are. Well, the thing is that on the sampling distribution, we know that 95% of the data points will be within 1.96 standard errors from the mean. And what that means, and you can actually see this down here, is that we have 95% confidence that our population mean will be between 49 and 51 in this case. So we know our sample mean, and using that, and using our knowledge of the sampling distribution, we can say we don't know our population mean, but we can be 95% sure that it will be between here and here. As well as that, another thing about that is that if we want to go even further and have higher confidence, we know that 99% of our means will be, there it is, 2.576 standard errors from the mean. And so once we know our standard error, now we know that we have 99% confidence that that real population mean will be within this range of two numbers. Now the final thing I want to show you here, and we're going to go back to 95 because statisticians most often use 95% confidence, is that there is a 95% chance that the population mean will be within this range, and therefore a 5% chance that it will be outside this range. A 5% chance that the population mean will be here or here. There you go. And so what that means is that there's a 5% chance of having a mean at the far end. There you go. The probability P is less than 0.05. And so that's what a p-value means. A p-value means probability, and if the p-value is less than 0.05, that means that whatever number you found is outside of the confidence interval. So the summary is that we don't actually know what the population mean is, but using these sampling errors, using the standard error and using confidence intervals, we don't know what they are, but we can make a very good estimate of what they might be. And what you're going to do now, and what I'd like you to do, is for different standard errors and different sample sizes, I'd like you to just play around with this and find out what the confidence intervals would be for different means.